Welcome to Advanced Data Analysis 2 with me, Erik Erhardt, Professor of Statistics at the University of New Mexico. In this video, I'll help get you started with Class 11 on writing and plotting model equations. So we'll scroll down to Class 11, and there is a markdown file here and two data files that we will save into our data analysis folder. Now, DAT1 is from assignment 9. It's the kangaroo data set, so I don't need to download that one again. But the second one is actually for class 12. We're going to get a sneak peek of the next assignment's data set using it here. All right, so let's go over to RStudio. We'll open our markdown file and knit it for class 11. We'll set the working directory so that if we run code manually here, we'll be able to see the results in the console. All right, we'll open this up in the browser and zoom in and read through it. All right, so I've got two data examples here. One is on the kangaroo crest width, and the other is on faculty political tolerances, a data set we haven't seen yet before. All right, and what I typically do in a normal year when we're in class together is we would actually plot the values. I hand out paper versions of this assignment, and you fill this in on paper so that you can draw some pictures. But I think to make things a little easier this year, we're not going to do the plotting, but I will show you what those plotted equations look like. Instead, we're going to focus on writing the fitted model equation and then showing how you can get separate equations for each combination of categorical variables in a two-way factor model. The second part of this assignment is to actually have regression lines. So you have a separate regression line for each categorical variable. And that is what analysis of covariance is. It's when you've got a regression model with numeric variables, numeric x variables, and categorical x variables. Okay. And I say that this is some of the most important skills of modeling, to be able to write down the model using indicator variables, interpret the model coefficients, solving for the predicted value of any combination of predictors, and plotting that fitted model. Okay, so this assignment is focused on this first part, writing it down, and this third one, combinations of predictors, and typically we'd be doing the plotting as well. All right, so if you don't recall what indicator variables are, please go back to the lecture notes and review that concept. I believe that is in chapter 5. All right, so kangaroo crest width, we've seen this data before. We read it in subset for using the crest width, factor the sex and species variables. So we've got our 3 variable data set in here. We've seen this plot before. This is what the data look like for the crest widths. We basically have roughly parallel lines. And in assignment 9, we concluded also that there was not an interaction. So there were main effects for sex and main effects for species. So that is the additive model that we fit, just additive on the 2 main effects. And when we do a summary of that linear model object, we get coefficients. And so we are going to be looking at this column of estimates. We have an intercept, we have an offset for female sex, and we've got 2 offsets for these 2 species, MFM and MFF. Okay, so you might be wondering, where is the male and where is the other species, the MG species? But of course, those are what's represented in the intercept. Okay, so our job now is to write the fitted model equation. And I've got just space for you to do that here. The second part is to write a separate model equation for each combination of sex and species, and we'll get to that once we've written this fitted model equation. All right, so let's go over to RStudio, and I'll scroll down to the point at which we fit the linear model and print out the summaries. Okay, so we're ready to write the equation, and I just want to scroll up a little bit to reveal this coefficients table. Okay, so we're going to write the equation right here. I'm not going to do any fancy stuff in terms of our programming to have these numbers automatically fill in. I'm just going to type it the way I see it. Okay, now I put these backslashes in there just to create some space because typically this assignment is handwritten. I'm going to remove those so we can just type our equation here. Now let's just focus on the content of the equation, and then we'll focus on writing the equation in a nice way. Okay, so the first thing you can do is just say, well, the response variable, if I scroll up a little bit more, we can see the call. So the formula is crest width, so that's the response variable, CW, equals, and then some function of sex and species. And the, whoops, I just pushed the down arrow and it jumped. Okay, so some combination of sex and species. So which terms are in our model? So if I scroll down just a little bit, the coefficients in this column, these estimates, are the only 4 terms that are in the model. And so now we just need to figure out how do they go in there. So we've got the intercept, 97, and I'm not going to care too much. Let's do just one decimal place. The intercept plus, now I'm going to write it fairly simply first, and then we'll tidy it up and improve the notation. But I'm just going to put the estimate, 24.7, okay, so that's this number here, times sex F. And I'm just going to start by putting in those using the variable names that are down here, and then we'll improve this. Plus 4.99 times this species plus 34.3 times the MFF species. Oops. Okay. And so that will get you at least half credit if you do that much. Okay? Now, the fitted model equation, I make a comment here. So use the parameter estimate table above to write out the fitted model equation. Use indicator function notation for categorical variables. So we still need to do that part. First determine what each sex and species number is. So in this case, we actually have the labels here, so we know what's what. I think this is an old comment from an older version of the assignment where I didn't label the species and sex with their labels and instead just had their numeric value. And I also say the equation looks like this. Okay, so let's follow that. We'll put it in dollar signs. Okay, and then the hat notation indicates that this is a prediction. Okay, so I'm going to put a hat around CW, and that's a pretty good start. Now we probably, what the heck, let's just knit this and see what the result is. Make sure that we always have a working version of this equation. I've written so many equations that I'm quite confident that I could do it without sort of looking, but it's better if we check it out. Okay, so this is what we've created so far. CW hat, the crest width hat, equals the intercept plus, and then we've got, each of our estimates times that term. Very good. So let's now make this a little bit nicer. And it's not going to take very much effort. Okay, so now we need some indicator variables. So the indicator variable here is So right, let's say something about the intercept. The intercept includes sex equals male and species equals mg. Okay? Or maybe represents. Sex, male, and species mg. Okay, so that's just sort of helps us understand, okay, so 97.8, that's the mean crest width for male species mg. Okay, these values, like 24.7, that is the difference for males, between males and females, of species mg. Okay, so what we need here is an indicator that if you are sex equals F, then this indicator variable becomes 1, which means we have 24.7 times 1, which means that this then gets added to 97.8, and that then is the estimated crest width of females species mg. Okay, so there this I takes values 0 and 1. Whenever the statement inside is true, it's a 1, otherwise it's a 0. So we're going to do the same thing for these others. 4.99 times an indicator variable where species equals MFM, and then the last one, an indicator of the species equals MFF. Now this equation is getting long, it's starting to wrap. I find it a little hard to read, that sort of thing, so I'm going to start formatting the equation now and make it a little nicer. I'll put double dollar signs before and after. I'll do hat crest width equals 97.8 plus the next term plus the next term plus the next term. Okay, I find that much easier to read. All right, let's knit this and see that we've got a nice equation. So you'll definitely get full credit for what we've done so far. Okay, nice. We've got crest width equals all that stuff. Perfect. So the last thing I can do is sort of make this a little nicer to read. All these italicized sex and species and these labels, those are, I think, a little hard to read. They're not right in an equation. The use of slanted or italicized characters typically refer to variables, and we don't really have variables here. We have these labels. So one way to improve that is you can do Textrm, which is meaning we want that text to appear in a Roman font, which just means that it's not going to be slanted. And we're going to wrap all of these with that. Make sure that I close all my braces at the end. All right, and I'm going to make maybe I'll make one more small modification. All these little details are just for you people who are going to be really interested in setting equations. Now, I think this is much nicer to read. I think I can still be italicized. It doesn't really matter too much, but and then the last part is this little hat is so small over crest width, and there is another character called wide hat. So if you change this to wide hat, it actually makes the hat wide enough to cover whatever it's covering. And so if we take a look at this now, we have a nicer hat over crest width. And I would say this is a pretty nice solution. Now you don't really need these multiplication signs. You could remove those if you wanted, but let's just leave it as it is. We've spent enough time doing that. Okay, so that is a nice way of setting that equation. And I really like this comment here about the intercept, because it makes it immediately clear to anyone who's looking at this equation, what does that intercept mean? Okay, so you've established what the baseline categories are. Okay, finally, or next, I guess, separate the model equations. So for each combination of sex and species, what is the fitted model? And I'm not going to worry about changing the y-hats. Let's just fill in the values on the right-hand side. All right. All right, so now we're going to do a little bit of math. So we know from earlier that this 97.8 is what you get for just the M and MG baseline group. Okay, so that I'm going to actually put that on every one of these, and then I'm going to add the offsets so that we can show our work. Okay, so the intercept is always involved in the equation. That's what we saw here, right? The intercept's always involved. So now the point is, pedagogically, what should I be showing? Is it, I think it might be okay if I'm working off of this little table down here. So let's work on that. Okay, so I'm going to now, so if MFM is the species that we're looking at, then species MFM is the offset that we're going to add. So we're going to add that value here. Okay, so males are in the intercept, so that's the baseline group. MFM is not in the intercept, so we need to add this offset. And if we go over to our equation that we wrote, let's think about this again. Okay, so we're this category. Let's work through all of the indicator variables and see if we get the same thing. Okay, so we've got male sex, so we have 97.8 plus the sex is female, that's false. So this indicator variable equals 0, which means this term is 0. Okay, next, the species is MFM. So species MFM, this is true, therefore the indicator variable equals 1. Therefore, 4.99 plus or times 1 is in the equation. And lastly, the species was not MFF, so this is false, so this whole term is 0. So what do we get? We get the intercept plus 0 plus 4.99 plus 0. And that is what I've written here. Okay? And then we can go through and do the same thing for each combination. So for the species, for male sex, species MFF, we get 34.3. Okay. The next three are the same, except we are now sex is female. So what is the addition for females? We have 24.7. So 24.7. And then this one is the MG group, MG species. That's the baseline. So that's it. If you wanted to, you could do sort of plus 0. Okay, all of these three are female, so I'm just going to copy this down to all of these. That affects each of them. Similarly, for the MFM group, or species, that's the offset for this one, 499. And for the MFF offset, that's the 34.3, which I copy onto the last one. I think if you leave it like this, that's probably full credit, okay? But I think it would be even better to do an equals and do the addition. Okay, the nice part about R is that it's effectively a calculator, or it's a very good calculator. So if I highlight this and press Control Enter, it will submit it, should submit it down here. Let's see if we can get that to work. Interesting. Control Enter. You know what? I guess it's not submitting it because it's not in a code chunk, but I can copy and paste. and copy and paste. I realize now I have not been consistent about my significant digits. The 4.99 should probably just be 5.0, but anyway, I'm not turning back now. If this was if I was preparing this for a manuscript, I would care more. Okay. There we go. Okay, so those are all the estimates. Let's knit this and take a look at that result. Okay, that looks pretty good, right? Yeah. So I don't care about changing the y hat to crust width. It's the crust width is the y variable. So we've got all of our estimates there. Okay. So what I would typically do in a year, like a normal year, is I would have you then plot those means here, and instead I'm just going to show you what that looks like. Okay, hold on, I'm just preparing something off screen, and that's good enough. All right, so the dashed lines are the observed means that that we plotted earlier, and the dark solid lines are the estimates from this model. One thing you'll notice in the dashed lines is that those dashed lines are not parallel. But the model that we fit, if I page up, had no interaction. So these lines must be parallel. And so the fitted equation does have parallel lines. The blue and the red are parallel here, and then they're parallel between the second two species as well. So we have forced, through our modeling, parallel lines because there wasn't strong evidence for non-parallel lines, and through the use of Occam's razor to provide as simple a model as possible that is not too simple, the simpler model one of parallel lines. And so these values that you see here, for example 97.8, where is that on this plot? Well, male is red, MG is here, so this point here is 97.8. Let's look at another one. How about this one at the bottom? Female MFF. That is 156.8. So females are blue, so it's this curve. MFF is the species. It's this top right, and that is 157 roughly. Okay. So that is that's the end of this first part. Let's move on to the second part. So you can see, boo-hoo-hoo. No plotting this year. Okay. All right, so the second example is different in that we have a numeric variable and a numeric predictor variable and a categorical predictor variable. Okay, this is a new data set, so let's read the description. A political scientist developed a questionnaire to determine political tolerance scores for a random sample of faculty members at her university. She wanted to compare mean scores adjusted for the age of each of the three categories of full professor, associate professor, and assistant professor. So assistant professors are sort of those entry-level professors. You get promoted to associate professors, and then you get promoted again to full. Okay. Also, I should say that these political tolerance scores, this is a very old data set. I don't know exactly how old, at least 20 years. So who knows if this reflects current, feelings about tolerance. But The data are given below. Note that the higher the score, the more tolerant the individual is. Okay. So, what would we, well, I'm not going to say what we would expect, but you may have your own sense of what you expect by age and by category. Okay. I guess one thing here that I should note is that these professor levels are associated with age, right? So you earn your PhD, maybe you do a postdoc or two, and then you get hired as an assistant professor. You're in that position for about 6 years. You get tenured and promoted to associate professor. You take a year of sabbatical, so that sort of took 7 years. And you get another 6 years as an associate professor. If everything goes well, you get promoted to full, and you take a year sabbatical. So that took another 7 years. And then you become a full professor, and you stay there until you retire and become emeritus. So these levels of professor are associated with age. Below, we will fit and interpret a model to assess the dependence of tolerance score on age and rank. And we're going to assess the model in a later assignment. The purpose of this assignment is just to plot what you get for the fitted model. All right, so we've got a data set. We make rank a categorical factor variable and re-level 3. What that does is it makes level 3 the baseline, and level 3 was assistant professor. So I just wanted the assistant professors to be the baseline because they're sort of the ones who are starting out. And then you think of 2 and 3 increasing order from there. A better way to have done this would have been to label these as assistant, associate, and full in that order. All right, so I'm going to fit the model now. I've got score equals age multiplied by rank. And the star operator, recall, expands out to an interaction model. So we've got age plus rank plus the interaction of age and rank, those 3 terms. And when we look down at our summary, we get our model estimates. So in this case, we don't really care about these p-values. We don't care about model assumptions. We're just interpreting the model equations. So we've got the intercept of 5. We don't really have a sense of what the units are or how big the units are, but so that 5 are going to be for rank 3, because 3 was the, recall up here, 3 was the baseline level, okay? And then age, the intercept is also when age equals 0. Okay, so for all those assistant professors who were born into their jobs at age 0, this is your predicted political tolerance score, 5.4. So really the intercept here doesn't have a meaningful interpretation. What would have been better is to maybe adjust age and maybe subtract 40 or subtract 50 or something, sort of the average age of a professor, so that this would represent sort of that average. Or maybe a typical age of an assistant professor. Okay, anyway, those are decisions you can make in order to improve the interpretation of the intercept, but would not affect anything else about the model. All right, so let's look at what what our equation should look like. So let's go over to R, and we'll do our work over there. Okay, we don't really need to plot that. We'll read in the tolerance data, we'll fit the model, and we'll have the model summaries in that column there. And we'll start to write the equations. So we'll clear this out, and we'll just start, we'll write the equation very simply first, and then we'll improve the display of the equation, but let's get the equation correct first. So let's first just say that the intercept is associate professor, assistant professor, so that's rank equals 0, at age equals 0. Okay, so that will at least ground our thinking about what that intercept means. Okay, so we've got, what should we have our score? Okay, so let's use the same names. Okay, so we've got score equals, we've got our intercept. Oh, let's not go crazy. I'll just type these numbers. 5.43 plus, you know what? Last time I reformatted these to be able to read a little more easily. Let's just get started with that right away. Plus, now we've got age. So we've got negative 0.0. I better take this to a couple decimal places at least. Times age plus 2.78. So really I'm just times rank 1. I'm just really just copying the numbers and then copying the variable. That's a nice quick way to get this done. 1.22 times rank 2 plus negative 0.07. Better take this to a second decimal place 2 times, age times rank 1. Cool, so that's where that interaction's happening. And we have 0.030 times age times rank 2. That's it. All right, let's make this a display equation by wrapping it in double dollar signs. And let's knit this to see that it looks okay. So now we're going to, when this is done, we're going to come back and we're going to replace all these ranks by indicator functions. Okay, so that looks like the equation, and the numbers correspond to the numbers up here. So I think we did okay. Now you might be wondering, what the heck, Eric? Why is there a plus and a minus? I don't care. So you can remove the plus sign if you want and just have the minus sign. It's also okay by me if you have a plus, a negative. That's up to you. In terms of just getting things started, I just put both, knowing that I could tidy it up later. All right, so let's work on our indicator variables. So now we've got indicator for when rank equals 1. We've got an indicator of when rank equals 2. And same thing for here, indicator rank equals 1. Wherever you have a categorical variable or a factor variable, you need to put in these indicator variables. Age is numeric, so that's the person's actual age, whether they're 30 or 40 or 50 years old. Okay, we can tidy up these minus signs if you don't like them. And the last thing would be to we should probably have a hat over score. Okay, and we learned from earlier that we can do a wide hat, and we can also make sure that score isn't all slanted, so it's a little easier to read. Okay, and I'm going to use the Textrm and wrap all of our other variable names in that as well. And I'm going to come back and close all these curly braces after I paste all this. Okay. Okay, we'll knit it and see if we're happy. Okay, this looks pretty good to me. I'll show you one more thing in LaTeX. This equation's sort of getting long, and you might want to break that equation in a specific place. Oh, but how do you do it in this $sign environment? That's in a nice way. Let's just try this. If you put a double backslash, that should put a new line in an equation. But I'm just not sure where this is going to line up, whether it's going to be left justified. I don't think it's going to be justified at the equal sign, which is really what we want. Sorry. Okay, it ends up not looking too bad because the first line is longer than the other. But, so, okay, I'm sort of satisfied with that. So we've got the intercept, we've got the slope with age, we've got the two main effects of rank 1 and 2, and then we have all of our interaction terms on the last line. Okay, good enough. All right, separate model equations. So now we've got to write an equation for each of our ranks. Okay, so let's go back to our studio and let's see, rank 1 I think was full, rank 2 is associate, and rank 3 is assistant. For some reason okay, that's what I want. All right, so let's figure out what our equation should be for each of these. And we can either refer to the equation that we just wrote. Yeah, let's do that. If we can get enough of this on the page. Okay, that'll work. All right, so let's start with an assistant professor because those are that is the baseline case. So we have, so basically I'm going to go through each of these terms and ask, is this indicator variable equal to 1 or is it equal to 0? And if it's equal to a 1, then I'm going to include the coefficient in front. All right, so the assistant professor is 5.43, that's the intercept, it applies to everyone, plus the age, everyone has an age, so that's negative 0.013 times age. I'm not going to worry about the formatting, I'm just going to type it. And then, what else happens? So if rank equals 1, well, rank equals 3 down here. So rank equals 1, that's 0. Rank equals 2, that's 0. Down here, rank equals 1, that's 0. Rank equals 2, that's 0. So these other four terms don't apply. So that is our equation for the assistant professors. All right, let's do the full professors next. So I'm going to copy all this stuff because it applies to everyone. Okay, everyone's going to have an intercept and everyone's going to have a main effect for age. Okay, full professors are rank 1. So anytime there's a rank 1, we have to include that term. So we've got the intercept, slope with age, we already have that copied down. Then we've got rank equals 1, so we have a plus 2.78. And if you want, you can say times 1, not really important. Then the next one is rank equals 2, that's false, so this is equal to 0, we don't include that. Then we have a negative 0.072 times age times 1, where rank 1 is true. So that equals 1. Then the last part is equal to 0 because rank 2 is false because we are at rank 1. Okay, I'm going to take away some of the extra stuff here. We don't really need that 1. We don't need this 1. All right, let's fill in the last one, and then I'm going to improve what this equation looks like. Okay, the last part is the associate. So plus, this is where rank equals 2. So same thing, but rank equals 2. We have intercept, slope with age. Rank 1 is false. So the next part is the one with rank 2, negative 1.22. Plus, the next one has rank is 1, that's false, so it equals 0. And the last one, rank is 2, so we need this one. 0.030 times age times that 1. Okay, great. So let's go ahead and knit this. I'm not going to spend any effort making these equations beautiful in this video. But I am going to do one more thing to make it much more readable. Okay, so here's our equations for full, associate, and assistant professor. Assistant professor is as good as it gets, okay? But look at full professor. We can do something with this right-hand side. How can we group these terms to make it much easier to read? Well, we have the intercept plus this offset of the intercept. And we could group those two terms together. Similarly, we have two terms that are multiplied by age. So we could group those together. So let's go over and do that work over in RStudio. Let's see. So equals, I'm going to copy this whole equation again. Maybe I'll do this equals inside the dollar sign. Okay, things are starting to get messy. Oh, I know what I'll do. I did put these extra lines of table down here, so I could just sort of copy this down one row in the table and redo it down here. I like that idea. Okay, so let's group some terms. We've got this value over here, which can be added to the intercept. And then we have plus that slope with age minus that slope with age. Okay, let's knit this just to go over and make sure that we like what I just did. And I don't think I'm going to go through all of these cases because I believe that you can do it yourself with this example. So for full professor, I just took the intercept and this 2.78 offset and grouped those together. And then for the terms multiplied by age, I've got the negative 13 and the negative 72. Okay, those are all together. Great. I'm going to do one more step. I'm going to set that equal to, and I'm going to add those numbers together and give you just a single value for that intercept. Okay, so this intercept equals, 8.21. I'm going to remove the parentheses. And the slope did that twice, is negative 0.085 times age. Okay, so now we've got the final nice equation for the assistant professor, which we did right at the beginning, and now for the full professor. Okay, so we can see that the intercept is quite different. We don't really care about the intercept because the interpretation is for a person whose age is equals 0, and not even geniuses attain that level of scholarship. And then we've got the slope. So it's much steeper with age for full professors than for assistant professors. So if you go through and do the same thing for the associate, you'll be all done. If you want to add the Textrm around age to make it more readable, you're welcome to do all that as well. Sort of a quick thing you could do in that regard is you could put your cursor down here and you could do replace age with Textrm age. Okay, this one's highlighted, so then I can just replace. And once it jumps to somewhere else, stop. Okay, let me show you what the resulting equations look like, since you miss out on that this year. Oops, not there. Over here. Okay, so I made age better to read. All right, here is what these equations look like. I'll put it on this, well, on this side. Okay, so we have score on the vertical axis. We have age on the horizontal axis. We have I've labeled the points using their numbers. You know what, I'll make this a little bit larger and zoom in a little bit. We don't really need to see the equations in the background. Okay, so the ones are the full professors, okay, which have this sort of a decreasing diagonal slope. We have threes, which are the assistant professors. They're the youngest. That's the one that we solved as the baseline case. They're most horizontal. And the associate professors have this slight increasing relationship. And those end up being the regression lines. I sent the axis all the way over to 0, because if you're plotting this, you really need the intercept to help you anchor the regression line. And so let's take a quick peek to see if these values make sense. The associate professors, rank 3, is 5.43. The associates are the red, 5.43 is right there, where age equals 0, 5.43. Okay. Similarly for the full professors, the green line, the intercept is a little bit over 8, and that's what we see right here, 8.21. Okay, so that would have been the last part of the assignment if this had been a normal year. All right, I hope that helped with getting this assignment going, and we'll see you in the next one.